All right, so these two formulas here obviously are identical except for the plus or minus, right? Same thing for these two, all right? What you're going to see, though, most of the time in maybe other textbooks, or if you're to open like a calculus textbook at the front cover, usually it's going to have a lot of your trig identities and just a lot of prerequisite formulas and stuff like that that you're going to need for that calc course. These will be written this way. It'll be like sine, and then a lot of times they use, instead of S and T, they'll use alpha and beta. So they'll say alpha, and they'll go plus or minus beta. Okay. Then when we rewrite, this is the structure that I remember for the sine. Okay. So sine will always go. Tablet died. Hold on. All right, so it's always going to go sine, cosine, and then sine again, but the sine here, the second sine that I say, is the SIGN, thank you, of what is right here, okay? So we're using a plus sign or a minus sign, and then so it goes sine, cosine, sine, cosine, sine. So if you can just repeat sine, cosine, sine, cosine, sine, cosine, as far as you need to, you'll actually end up saying sine 3 times, okay? You then have the correct structure. Is that okay with everybody? Okay? And then if you go back, so I didn't put the angles in, but if you go back, the angles are in the same order that they show up over here. So we go alpha, beta, alpha, beta. And we developed our sine adding and subtracting formula, okay? If you want to do cosine, it's the same process. I go cosine, alpha, plus or minus beta. Now cosine this is the way I remember this one. It goes cosine, cosine, cosine. Okay? Co kind of meaning opposite in that situation. Does that make sense? Okay? Or maybe the complement sign. Does that make sense? When I have a complement of something, it's everything else, right? If I say, all the people in this room are a set of objects, and then I say, remove Mr. Fay from that set, the complement would be all the students that are left over, right? Does that make sense? So if I'm using pluses and minuses, I say plus, then the complement of that is minus, right? Okay? So it goes cosine, cosine, complement sine or cosine, and then finishes off with sine, sine. Okay? And then we go back through, in the order that we saw our angles here, it's alpha, beta, alpha, beta. What I want to draw your attention to, if you're going to write these, basically writing these two formulas together at once, using this structure, look at those two symbols. They are different, are they not? One has the plus sign on top and the minus on the bottom, and the other has the minus on top and the plus on the bottom. So when I'm reading those as two separate sum and difference formulas, the symbols on top and the plus and minus go together in one line. So it's alpha plus beta, then in the expanded version it's a minus sign. If it's alpha minus beta in the compact side, and on the expanded side, it's plus. Okay? Is that something we can remember? So sine, cosine, sine, cosine, sine. And then cosine, 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 sine, sine. Okay? I'm not going to deal with the tangent right now. We'll talk about those on Monday. Provided we get through the proofs of these in time to do that. But just think about this real quick. If I want tangent of, say, alpha plus beta, isn't that going to be sine of alpha plus beta divided by cosine of alpha plus beta? That make sense? Sine of alpha plus beta, that numerator is going to look like that. The denominator is going to look like that. Okay? And once we divide those two things and do a little bit of algebra, there's a convenient division that we have to do, we end up with tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. And we end up with that tangent sum rule. Okay? And the same thing will happen with the difference. So we'll talk about that next week. But the idea is, guys, throughout the entire course, when we come across formulas for tangent, my hope is that we don't remember them or we don't memorize them, because you already have the relationship that tangent is sine over cosine, and hopefully we're refining our skills of working with these identity type questions that we can make substitutions, and eventually our tangent formula should kind of fall out of those processes. All right, so what is this actually doing for us? Okay, well, alpha and beta, or in this case S and T, those are being put into the argument of the sine, cosine, right? That means that those are an angle. S plus T is, when we sum them together, it gives me an angle, okay? S and T individually are the two smaller angles that make up that total. So let's say, for instance, let's just do this. Do you guys know, we'll do one that we are pretty comfortable with. If I say cosine, let's do sine. Let's do sine of 60 degrees. Do we know that that is sine of maybe 30 plus 30? Does that make sense? Where S is 30 and T is 30. So can I rewrite this as sine of 30 times cosine of 30 plus cosine 30 sine of 30? Now here's my quote. We know sine of 60 is radical 3 over 2, right? So when I'm done with this, what should it end up giving me? Radical 3 over 2, right? It should give me the same thing. What is the sine of 30? 1/2. What is the cosine of 30? Radical 3 over 2. Plus now, what is the cosine of 30? 1/2, right? What's the sine of 30? Radical 3 over 2, right? I got those backwards. Cosine of 30 is radical 3 over 2. Sine of 30 is 1/2. But does it matter? No, the way I've written it, the multiplication is commutative. So when I do that, okay, can I take a radical 3 over 2 out of both of these and then be left with 1/2 plus 1/2? What's 1/2 plus 1/2? 1. What's radical 3 over 2 times 1? Radical 3 over 2, right? Okay. So, do you see that sine of 60 equals sine of 30 plus 30? We can do it that way? Now, obviously, that's kind of trivial. We knew that answer to begin with. We knew that result off the unit circle to begin with. There are others on the unit circle that we don't know. Like, let's say, sine of 75. Okay, sine of 75. Do we know that off the unit circle? No. Okay. But give myself a little bit of room here. Sine of 75 what are two angles on the unit circle that you can add together to give you 75 degrees? 45 and 30. So I'm going to rewrite this as sine of 45 degrees plus 30 degrees. So those are my alphas and betas, or S's and T's, whatever letters you want to use, right? So sine turns into, so sine of a sum is sine, cosine, sine, S-I-G-N, cosine, followed by sine. And then I go back and I plug in the 45 and the 30 in the order that they showed up in my argument. So this is going to be 45, followed by 30, 45, followed by 30. Now we evaluate. What is the sine of 45? Radical 2 over 2. What's the cosine of 30? Radical 3 over 2. Plus then, what's the cosine of 45? Radical 2 or 2. Times the sine of 30. What's the sine of 30? 1/2. Can I multiply those together? Radical 6 over 4, right? Can I multiply these together? Radical 2 over 4, right? Is that a common denominator? Radical 6 plus radical 2 all over 4. Okay? That is the sine of 75. Now, grab your calculator or whatever you use, GeoGebra, Desmos, whatever, and I want you to take your calculator, put it into degree mode, go degree mode, and type in sine of 75. So sine, show my mode degrees. Sine 75 gives you that decimal right there, right? 0.9659. Is you agree with that? Okay. So then, type in the square root of, you have to do this in parentheses up top. Square root of 6 plus square root of 2, and then divide that by 4. And what you recognize about those two values? They're the same, right? Okay, so we now have the exact value of what sine of 75 is, or exact way of determining that value of sine of 75. It's the ratio of the opposite side divided by the hypotenuse of a triangle that has a 75 degree angle in it. Does that make sense, everybody? Okay. So if we wanted to, I mean, this is a situation where, you know, we've got our special right triangles, the 30, 60, 90, 45, 45, 90, right? We could have another special right triangle that's 75, 15, 90, and then this would be the ratio between the sides and the hypotenuse. Does that make sense? Okay. The opposite side and the hypotenuse, and then we could find the adjacent side through a little bit of algebra. Obviously not something that we want to deal with a whole lot because that's kind of nasty. But I think it's important to visualize what these things mean. Okay? If I look at the unit circle here, I've got this thing traced out to a 75 degree angle. Let's see if we can change the font size a little bit for you. Okay? So I've got this angle traced out, this arc traced out to 75 degrees. Okay? And point M is where my cursor is. If we look at that point M right here, so this right here is the sine of that 75. Does that make sense? Okay? So this is ultimately providing me the ordered pair on the unit circle for 75 degrees. That was the y coordinate. Can we find the x coordinate? The x coordinate, this 0.258 number, can't that be found by taking the cosine? Let me move this up. Get rid of this work. Let's do cosine 75. Cosine 75, would you agree that is cosine of 45 plus 30? Is addition commutative? So could I have written this as 30 plus 45? Yep. And then I can go, so this is cosine. It'll be of 45. So it goes cosine, cosine. Cosine, so this is a plus. So this one's got to be a minus. And then it finishes off sine, sine. And now let's evaluate that. What's the cosine 45? Radical 2 over 2. What's the cosine of 30? Radical 3 over 2. Minus the sine of 45. Radical 2 over 2, right? What's the sine of 30? 1/2. Multiply that out. We get radical 6 over 4 minus radical 2 over 4, right? If we take that onto our calculator, I'm just going to copy that, go back and edit that sign there. I get 0.2588. And that's exactly what our applet here was telling us that cosine value should be. Is that right, everybody? Okay. I don't know if this will do this. Let's go surd text cosine of 75. No. All right, so this point here, guys, on the unit circle. So now that we have this point, let's go, let me show that object. That point right there is now a radical 6 minus radical 2 over 4, comma, radical 6 plus radical 2 over 4. We now have the ordered pair for that point. Does that make sense to everyone? Okay. Now, because of symmetry and how symmetry exists, would we also know then the ordered pair for 105 degrees right there? So it'll be the exact same coordinates except for the x1 is negative. Okay, so put a negative out front, or distribute that negative through, and it would be root 2 minus root 6 over 4. Does that make sense, everyone? Okay. Now, I'm not going to ask you to memorize those. I'm not going to ask you to memorize around the unit circle those ordered pairs, because that's going to be very troublesome, I think. It's going to be hard. But I am going to ask you to know the sum and difference formulas so that you can generate those when you do need them. And the idea is that we don't use, if we use 75 degrees a lot, it'd be something probably that we want to remember off the unit circle. We use 30 and 60 and 45 a lot, so we remember them. Okay, we develop the relationships with them. If I need 75, the idea is grab this formula real quick and generate it. Okay. Now, think about the unit circle. Are there any other angle measurements up there? Keep doing that. Are there any other angle measurements up here that you can put together to make 75? Can I add or subtract any other angles to get 75? Can I take 210 and 135? If I subtract those, do they give me 75? Okay. So what this is saying, and I'm not going to do it because we're running out of time here, what that would be doing, it says, okay, if I could take the cosine of 75, rewrite it as the cosine of 210 minus 135, and know the sine and cosines of 210 and 135 accordingly, I should get back the same exact thing. Does that make sense? So you might be doing cosine of 75, that's 30 plus 45. Your neighbor might be doing cosine of 75, 210 minus 135, and you're both going to arrive at the same conclusions. Okay? So it doesn't matter, whatever values you know off the unit circle that you can add or subtract to get the desired angle they're asking about, use them. Okay? There is one here that I think is troublesome for some people, and it's this one here. It says cosine pi over 12. What is different about this one? It's in radians, okay? And now, if we go to the unit circle, the radian measurements are all thirds, fourths, halves, and sixths, right? Do we want to kind of sit there and think about, okay, which ones do I have to add together to get 12? Probably not the same but, right? What can I do with that pi over 12, though? I can convert it, okay? And it's very simple, very quick to convert, okay? Two ways of knowing it. Either we know that pi over 6 is how many degrees? Pi over 6 is 30 degrees, right? Isn't pi over 12 half of that? So pi over 12, 15 degrees? Or you can go back to what we learned the first day. Multiply by our conversion factor, we get 180 over 12. That does give me 15. So now I go cosine of 15 degrees. That's the question being asked now. Okay? Do not do these with radians. You're going to spend so much time more time than necessary, and trying to figure out which two radian measurements go together to add or subtract to give me pi over 12. Or if I change it to degrees, it's then obvious I'm going to take what values to get 15. Okay, 45 and 30. So 45 minus 30. Was anybody thinking 75 and 60? Because we now know cosine 75, right? But cosine 75 is kind of uglier than cosine 45. Okay? So now we just go cosine 45, cosine 30, plus sine 45, sine 30. We go through and evaluate cosine 45, radical 2 over 2, cosine 30, radical 3 over 2, and we get radical 6 over 4 plus radical 2 over 4, right? And that's the cosine of 15 degrees right here. So if I was to write an ordered pair, it'd be radical 6 plus radical 2 over 4, right? How does that cosine right there relate to that sine? They're the same, right? So what do you think this y value here is going to be? That y value there is going to be that y, or that x value, right? Because 15 degrees is the inverse angle across the line y equals x of 75 degrees, isn't it? Or maybe we think about it as being the co-angle, the complementary angle, okay? So that's kind of the relationship that's existing there with those, okay? So I guess doing that example just to prove, don't ever deal with the radians. Change everything to degrees because you're more comfortable with that anyways, and work through degrees. The last one, the last type of question I want to talk about today is this one here. So this is giving me the expanded side, right? I have to come up with the condensed side. So this goes cosine, cosine, and then sine, sine, right? So what structure is that? That's cosine. And now cosine, how do the signs that are between, how do they relate? They should be what to one another? Opposite. Okay? So then I have alpha being 14, beta being 46, right? What does that actually turn into? What's 14 plus 46? 60. So we're at this here is actually asking what is the cosine 60? Well, we know the cosine 60 is what? 1/2, right? If you type in on GeoGebra or Desmos, whatever you want to use, or your TI 8384, if I go cosine of 14, cosine of 46, minus sine of 14, cosine of 46, gives me back 0.5, right? Okay. Not necessarily sure why. I have to investigate why that's giving me a decimal that is not specifically 0.5. That's the idea. That should work. Okay. Is that doable? All right. So Web of Science 10.2 is open. I think right now I've got to shut it off on Tuesday. We'll talk about where we're at on Monday with it and go from there. I'm going to try to get some time allotted later in the day to try to work on your tests and get those in. Hopefully you did real well on them and I can grade them real fast. Yeah, I ate that. Good.